All right. Record is on now. So let us resume this problem. Okay. Now we have analyzed the structure. We have all the internal forces and everything. So it's time that we say complete the step number 3 and 4. Okay. So step number 3 and 4. It's the calculation of zeta A and zeta AA. Okay, so I have 3 portions so that you can see that. This time I need to break this A, B, and C. Okay, so the portion AB, the big M, which is the actual moment. This time it's just 10x, right? Now be mindful. This load 10 is creating the clockwise moment. And when you look at the virtual case now, you have the reaction creating the clockwise moment, and the moment that we apply, it's now in the counterclockwise direction. So our equation for the small m or the virtual must be account for that. Now it's going to be 1/5, which is the load, multiplied by x minus 1. Okay, and the range is from 0 to 4. Okay, range is a little bit crooked. Let's move that up. Okay, right. So now portion BC, and okay, portion BC is now this portion, and like I always do, you know, I want to maintain the only one equation that I can use for the virtual case, which is here, because you all know that you're going to have to do another integration for the small m multiplied by small m. So if I can write only one equation for this line, that would be beneficial. So by doing that, I'm trying to write the moment for the actual case by using the x from the origin for the portion BC. Okay, my x will begin from 0, so that I don't have to change the moment equation for the small m. Do you follow that? So for the portion BC, I will write the moment for this portion, but my x starts from 0. Okay, so that is going to be 10x. But this time, oops, sorry. My x must be minus 4. Oops, that's not, sorry, that's a mess up. 10x is correct because I begin from that. But then minus 50, that is the one that has to be multiplied by x minus 4. I'm sorry. Okay, and let's move this a little bit. All right, and whenever you face a situation like this, because you see, even I got confused. So after you got the equation, it is always a good idea to try to plug in the number and see what happens, because we want this equation to be available from 4 to 8, so that we can use this same equation of x over 5 minus 1, you know. So after we got this, you should plug in x equal to 4 into this. And when x is equal to 4, this second term is gone, right? So that means, yep, the equation looks promising. And when you substitute x equal to 4 here, you got 40, which is exactly the moment at this location. The moment here should be 40, right? And then you plug in x equal to 8 over here. So now you got 80 minus 200. So that's minus 120 over there. So that equation appears to be correct. Okay. And now the last portion, CD, and let me write DC so that you know I start everything from the free end D. And now we have 20, let's say, because I prefer to look at the beam or the frame from inside. That's how I do it. So if I stand here, I should use this one, or maybe this one. If I stand here and look inside, I see this as a positive moment going up, and I will see this as a negative moment coming down. Okay, so because this one is, if I was inside here looking at this direction, this one will get me negative moment. So it becomes minus 24x. Okay, but then that means this one will give me the positive moment of 3x over 25. And the range of the member is 0 to 5. Okay, is there any question? Now this example is useful when you look at this load. It just goes to show that you need to use the load that is perpendicular to the member and the actual length. Okay.
Teacher, can you explain again why 24 is minus?
Well, actually, it doesn't really matter, but I use a minus because I position myself here. This is my eye, eyelashes. When I look at the frame from this inside, you know, I will see this one from this direction. And when I see this one from this direction, I see this, this pink load is moving this portion down. So I can see that as my negative moment. It doesn't really matter because you can also move your eye out here and look. And when you look from this direction, this one is going to be your positive moment, but then this one will be negative. So it depends on how you look at it. But see, the point is you must be consistent. Because if I place myself here on the left side and I see this as a negative moment, I must place myself here as well. And this must give me the positive moment. But if you don't like that, you can place yourself here. And, you know, this will be a positive moment, but then you must place yourself there as well. And so this will be your negative moment. So you see where I'm getting at? It doesn't really matter where you want to do, but you must do it consistently. The point is be consistent with your sign convention. It doesn't really matter where you don't have to write the eyes like this, because you can see that this load is going up, but this load is coming down. See, this one goes up that direction. So it must produce the, let's say, if this is your point of reference, this produce clockwise moment. Then this produce counterclockwise moment. So it doesn't really matter which one you say it's positive. The other one must be negative. Right?
Okay, teacher.
Okay, that's a useful question. And the sign convention is something that you can't get away from. You must find your very own peace with it. Find a way to deal with it. Okay? And be consistent. So is there any more question? Thank you for asking.
Excuse me?
Yeah, sure.
Okay. Could I use the value from C to B? In this instance, you use B to C, right?
Of course you
If I
can, but
want to
from
yeah.
C to B, you will have the constant moment.
Yes, yes.
So for me, it's a little bit more hairy because you got right.
Yes.
If you begin your integral or integration or equation rather from this point on, remember you also have the shear.
Oh, okay, I see.
Yeah, shear is not going anywhere. I am too casual in not write the shear down here because I know I'm gonna write the moment equation from left to right. So my
okay.
Maybe
and all the time, please bear in mind that it will have a share, right? So if we can first start.
Of course, you must always have that. So here you got 40, right? Otherwise, it's not equilibrium. And here you got 1/5. So actually, it's good that you asked because I did not complete my free body diagram. If I completed my free body diagram, you would have seen that it's not a good choice to start from right to left because now you would have both the constant moment and the shear. Here you would have the constant moment and the shear as well. So to give yourself an extra term in your moment equation, think about, you got an extra term here and then you get another extra term there. When you multiply,
yeah, it's like the same,
quite
right?
a few more terms, right? In your integrals.
Okay,
so,
okay.
Be mindful of that. But it's good that you asked. You would not have asked if I had completed my free body diagram. So if you could see this, you would be able to plan ahead what kind of moment equations you should write and where to begin. Hang on. Okay, so it's good that you asked. Now we clear that up, and where you should pick up your point of origin for your moment equation. Sometimes it's pretty much based on your experience. So I strongly suggest that you do quite some practice until you see the picture. Okay, so now after we get this, let's carry on our, let's say, dirty work. Okay, so now theta A. That would be integral from 0 to 4, 10x multiplied by x over 5 minus 1 dx over EI plus another integral from 4 to 8. This time I'm going to use the bracket 10x minus 50 x minus 4. You see, well, let me complete this first. And then multiply by x over 5 minus 1 dx over EI. And then the last term, integral from 0 to 5 minus 24x multiplied by 3x over 25 dx over EI. Okay. Okay, so quite an annoyance with the kids. Okay, so and you may have a question yourself because this term looks a little bit hairy, but if you don't want to do this, it means that yes, you may want to start your moment equation from this point, but then you must realize that if you want to start from 0 to 4 from B to C, you cut the free body diagram, you have the shear and you have the moment as well. And you must do the same for this portion, and you will have the shear and then the moment as well. Be mindful of that. Okay. So your choice will, affect your performances, especially if you make it harder than it has to be. So, okay. So now from this on, I can get the answer. This is going to be equal to minus 232 over EI. Let me skip the self calculated integration part. Okay, which is the same, not more. Okay, and now we carry out the calculation of the rotation of the virtual load case. Okay, so now we carry out the calculation of delta AA. This is the rotation at A due to unit moment at A. So because of this sacrifice we made here, now I can wrap up the integral into 1 from 0 to 8. And my equation is x over 5 minus 1. Remember, this is for the both actual and virtual cases. So it's square now. Dx over EI. I can show off the chain rule integral here, but let's skip that, okay? And then we have another integral from 0 to 5. This time 3x over 25 squared dx over EI. Okay, and this gives us 2.63 over EI. So yeah, after this, now it's compatibility in step number 5. Hang on. Okay, so now the 5th one is a compatibility. Okay, so now we have zeta A plus zeta AA multiply MA equal to 0. Now we have minus 232 over EI plus 2.63 over EI MA. So now as the part switch, now we have MA as a positive value of 88.32. The unit is kilogram meter. Okay. Now the major difference is only here. See, this integral will become negative instead because now the direction here is a little bit in the opposite direction as the moment. Okay. But in the end, this gives us the positive moment in the end because it means we assume the correct direction. This is positive, not because we have the positive moment. The moment itself is a negative moment, but this is positive because it's in the same direction, that's my direction, okay, as the applied unit moment. Okay, so again, we can use the superposition to calculate our reactions.
Question, sir.
So you, hello, yeah.
I barely remember that you said that for this structure, this kind of structure, the reaction will depends on E and I, but as I can see, it is
because they cancel each other out in the end.
yes, it as long as
Good
that
question,
is
you
a
know.
constant throughout the beam.
Let's
it's not
see
different.
if I change EI of one member. Say if I change this member AC I so that I have 2 EI for member AC, what would happen?
No, it's no longer cancel out. It's going to be a ratio.
No longer, but you will have the effect of the fact that member AC has larger EI in your integral here, right? Here and then here. So these numbers will change. Again, the final result may or may not change, but in the system more complicated, surely it will change because you know the displacement of the member depends on EI, correct?
Yes.
And if I keep increasing, and if you have more than 2 members in the system, the reactions and so will be affected much more dramatically. Right?
No.
So you can see, yeah, and if I change again from 2 EI, it's like, okay, you know, we need stronger structure. I change this to 4 EI. You think the results of integral will change? Of course it will. But that's how I can say the EI will now affect the behavior of your structure. If this is determinate structure like this, I can change the EI all I want, but the magnitude of the reactions will remain the same, but the displacement will change. Right? Displacement will change, but the reactions will remain the same if my system is determinate. But now that my system is indeterminate, if I increase EI of AC, my reactions will change.
So if as long as it's constant throughout the structure, no matter how big EI is, it's gonna be the same reaction.
It's kind of dangerous to conclude that, but I see where you're coming from. You know, let's say because they cancel each other out. But if EI constant, it means that, you know, it doesn't really affect the structure. Yes, but maybe it's not. Yeah, if it's constant, maybe we need to do further analysis. But yes, let's say if we increase the size of the structure, or if we change the material, it will affect the behavior of the structure. Let us settle on that, right?
Okay, so at this level, it's not that safe to say that it is going to be the same.
Maybe it's pretty safe to say if EI is constant, but what you can say is this: if you change the E or I of the indeterminate structure, the behavior will change.
Okay, I see.
Right? Good point. Very good point. But if I in the opposite way, regardless of what I change in the determinate structure, it will not affect the force. Because you never use EI in the calculation of your statically determinate structure at all. That is evident enough, right? And you will see it much more in the structural analysis number 2, that when we are dealing predominantly with the indeterminate structure, it's all about EI. Okay, but a very good question indeed. So We still have 10 minutes to go, so I can probably finish this. So again, the next is just to complete the analysis of the structure. Okay, so now we can calculate the reaction by summing up the two cases together. First one is this one. We have 10 here, right? Right here is 40. That's 50 plus this one. Now we apply the moment here. 1, and then we have 1/5 going up, and then another 1/5 coming down here. So when we get that the moment is equal to this, we multiply everything we have on this by this, right? So if this is 1 causing this a reaction of 1/5, and when your moment is 88.32, then this reaction is going to be equal to 1/5 multiplied by 88.32. This is 1/5 multiplied by 88.32. Okay, so that means in the end, 1/5 of 88.32. That's roughly it's 17.66. So when you combine them, am I running? Okay. If you combine them, now you have this structure. Okay, so that means not here we have 88.32 as a moment. Let me change the color so that you see it better. Okay, now the reaction here is you got 10 and 17. So right here is 10 plus 17.66. That's equal to 27.66. Superposition. Okay. Here is 50. Then here is 40 minus 17.66. That is 22.34. Okay, and now we can proceed to draw the shear force and bending moment diagram if we wish. Okay, so that first portion right there. I wonder why I cannot draw a straight line anymore. So that's 50. That's a moment 88.32. That's shear or the reaction 27.66. So now you know this is going to be 22.34, right? And this moment, it should be the negative moment, okay? And this moment is going to be equal to 50 multiplied by 4. That's a distance, right? And then minus 88.32, okay? So 200 minus 0.88, so that's 100. Oops. Sorry. It's strange. I forgot this one. Sorry. Yeah, nobody's telling me at all. It's a bit strange. Okay, it's all messed up. Sorry. Oops. Okay, let's do it again. Okay. Let's start from the rim. So it's minus 88.32 plus 27.66 multiplied by 8 minus 50 multiplied by 4. So that's correct one. Okay. And this at the end, the number is minus 67.04. Unit is kilogram meter. So that's a complete free body diagram. And the second one, let me try it here so that you can see it all together. Now we need this load, right? We need the one perpendicular to this. So again, if this is our angle, this should be our angle. So this load is 22.34 multiplied by cosine theta, which is 3/5. And this is equal to 13.4. Okay, that's 13.4. And then if you calculate this, you would know that this moment is, of course, multiplied by 5. You got that 67.04. Okay, so the shear force and bending moment diagram should be a piece of cake now. Okay. All right, so for the first one, shear force diagram is simple as that. $27.66 minus 22.34, and your bending moment diagram is right here. This is SFD. This is minus 88.32, and then again this area is bringing the positive moment, and it's large enough to bring this one to the positive value of 20. Wonder, it's the same number as the shear, 22.34, and then this negative area will bring this moment finally down to that value, which is minus 67.04. And the shear force and bending moment diagram of this member should be a piece of cake, right? Just a constant shear and then just a basic triangle. So do I need to do that? Let's do it for completion anyway. It's a shear, and then that's a moment. Okay, so that's it. Is there any question?
No, teacher, but have a minute of the time.
Let me stop the record first.